Hi, this is Sean Murphy of SK Murphy. I'll be your MC for today's PATCA briefing on Rust, a modern systems programming language. PATCA is the Professional and Technical Consultants Association. You can learn more about PATCA at patca.org. The best way to get started is to join as an associate member for $50. You can contact me at skmurphy@skmurphy.com if you have questions. We're fortunate today to have a briefing by Jerry Rice. Jerry has been programming professionally for more than 4 decades. He has used languages including C, C++, Ada, and .NET C#. Today, he will share his perspective on Rust. Please use the chat feature to ask questions during the presentation. We'll have an extended session after the end of the formal presentation. Jerry?
Yes, hi. Welcome, everyone. Um, so I'm trying to do this presentation in a way that folks who are not Rust programmers or possibly even other types of engineers or professionals other than programmers will get value out of it. But if there are a few people dialing in that are programmers or especially Rust programmers, hopefully it will have some interest to them as well. So let me get going here. Basically, Sean covered this, but we'll do a short embedded demo at the end of the slides or near the end of the slides, and then we'll make the slides available following the meeting. If there are some slides after the demo section that we may or may not have time to cover, it depends on the number of questions. So they'll be there. They talk about things in Rust that are being considered for future changes, and also for some tips about when you might consider using Rust for a new project, and also what what the issues to consider before doing so. Obviously, you'll have your own views on that, but I'll share some of mine. Okay, so Rust, for those who aren't familiar, the concept of Rust started in 2006 when this gentleman, Graydon Hoare, who was a systems programmer, still is a systems programmer, but not at Mozilla, but he was at Mozilla, and he started this project after working with C and C++ for a period of time early in his career because of the some of the difficulties that come up there. So he decided to create some new difficulties, but also solve some problems as well. In any case, that he started that as his own personal, open source project, and then he shared information with his colleagues at Mozilla along the way. And then that in 2009, about 3 years into it, Mozilla, the open source organization, decided to fund it as well, and they funded it until 2020 when the pandemic was going on. They had some financial cutbacks, and they had to cut back their support quite a bit. And subsequent to that, the Rust Foundation was formed as a nonprofit by the community that had arisen around the Rust language in the open source world. So the first official Rust compiler was released. The first version 1.0 was in 2015, and then for the next several 3-year periods, new editions, which are sort of major releases of the language, were released. That was 2018, 21. And the last one just actually released last month in February, and it's called the 2024 edition. And we'll talk about that a little bit later, what editions do for us and for the people the organizations that use it. So anyway, Rust is a high-level programming language, but it's designed to be suitable and usable for developing firmware and operating system level modules, such as operating systems themselves, but parts of operating systems, drivers, kernel modules, and that sort of thing. It's also found use in over the past few years in infrastructure applications, things to do with cloud computing, network stacks, distributed software systems, cryptography, safety critical automation, which is a relatively new area for it, but it is a thing. And also aerospace and defense applications. As probably everyone here knows, really the C programming language and in part the C++ programming languages are really the only high-level languages that are available for programming low-level systems, applications. C++ is not necessarily the ideal approach. It's got some problems, which we won't go into here in any detail, but anyway, one of the nice things about Rust from a technical and a business perspective is that it's designed so that the language itself can evolve and improve, and newer versions of it can come out without abruptly obsoleting code that's already been developed in the past in Rust. And I think everyone who's been around the business knows that that's always been an issue with languages, and I think Python is a classic example of that, going from Python 2 to Python 3, and even some finer grained steps throughout its life cycle has been very painful. Similarly with C and C++, there's been some problems there. Also, when you want to install the Rust toolchain, of course it's free, like most languages are these days, but you can download it to your desktop, and it's supported on the major desktop platforms, Windows, Linux, and Mac OS. And there's a lot of software that's available on the web through these repositories. And the Rust terminology refers to its support libraries as crates. So the term crate is synonymous with library. And speaking of the free software that comes with that environment, with the Rust ecosystem, the Microsoft Visual Studio Code, or Microsoft Visual Code, is a very powerful cross-platform IDE that works very well with Rust. And then there's also, if someone wants to look at all the hundreds or thousands of crates that are available, they've been published over the last 7 or 8 years, they can go to this URL here at the bottom of my screen. It's crates.io, and it's they're well documented in terms of what they are and what they do, and the source code's available if for someone who really wants to dig into them. And now I'm going to bring up a sample Rust program just for those who haven't looked at Rust before in detail. And Rust is a functional language, not a pure functional language. It doesn't it doesn't have the restrictions that a pure functional language does, but it does ascribe more to the functional approach to programming than the traditional object-oriented procedural. Although it does obviously have procedural programming, as you can see here. And the main benefits of Rust are its safety, its type safety and concurrency safety, where the compiler, when you build your code, it automatically detects any situations where you've created code that would otherwise create dangling pointers or data race conditions. By analyzing the code and through its own semantics of the language, it can detect those situations where and will reject and give you error message saying, this is why your program is unsafe. You need to change it. Here's a suggestion how to change it. So this program here, Rust does allow local function declarations. Like here, this is a function declaration within a function, so it limits the scope of the function. but also it can also appear at the global level, like all other languages. But this function returns, and you'll see here it doesn't have the return statement. There is a return statement. It's not used here. In a Rust function, the last executed statement / expression, if it's not terminated with a semicolon, will return that value as its return type. In this case, it uses the built-in Rust type I32, which means it's a 32-bit signed integer. I'm not going to teach people the language here. I'm just giving you some flavor here. Don't think I'm going to go through the whole language, but I do want to give some context. So in this case, this function is returning the constant 47. It could be an expression 47 times 52, whatever. But here on the next line, we're defining an array, and it's an array of integer 32s. And this is the static initializer for it that's created. This is created on the stack of this function. And these values here are actually statically calculated at compile time. Even though this is a function call, the Rust compiler, as part of its efficiency optimization techniques, actually compresses this function call and calculates, in the case, because it's all constants, it actually embeds. I looked at the assembly language for this before when I was setting up this code snippet after compiling it, and it actually gets rid of this function call and hard codes 47 here. So that should gives you some concept of the level of efficiency and code generation that Rust provides. It's designed for that. That's what its sweet spot is, efficiency. So anyway, these things that end with a semicolon are macros, and Rust has the macro facility, which I'll mention in a later slide. Go into a little bit about that. But essentially, with this program, I'm going to go to the next slide. You can look at this later. The slides will be available. Let me go here. I've compiled. I've used this cargo command to compile and run the program. This is the output from that program. So you can look at that too. We won't go into that in any detail. We need to move along here. Okay. I should mention that the Rust software, the open source software, is all well, I shouldn't say all. Privately, anyone who contributes software has the option. They can license it any way they want. But the convention within the community, the Rust support community, and 99.8% of all of the thousands of packages out there are licensed with MIT and/or Apache licenses. And what this means is that they can be, those packages and even their source code can be adapted. You can use it in your own applications without any restrictions. And you can decide to publish it open source if you want, or you can publish it if it's a proprietary program that you're writing for your company. You can keep it closed source, and that's just the way the rules work. Okay, so this is another segment of that, and let me go here. Sorry, I'm following my own slides here, so I'm not as smooth as Sean is. He's a real pro at giving these presentations on Zoom. So these are the components of the Rust toolchain. There's Rust C, which is the actual compiler. There's Cargo, which is the build manager. There's Rust Up, which you use when you want to upgrade to the next new or the latest version of the Rust toolchain, which actually gets refreshed or updates every 6 weeks. And you can update to the newest one. And you can do so without fear of breaking your existing code or projects. Clippy is a built-in Rust toolchain lint static analyzer that you can use if you're wanting to see. It will show you things not only that the compiler would tell you if you compile, but it'll show you more things that the compiler won't necessarily emphasize that you might want to be aware of. So it's a nice tool as well. Then there's the Rust format. All the Rust crates or whatever, they get published to the standard crates.io registry, which anyone can do. Of course, you have to follow the procedures to do it. But all of those have documentation which is generated from the source code. Of course, the programmer who does that puts in annotated comments, that are like special comment brackets to include those comments. And those comments, it's customary to put them in there. And then not only does it help you with your software, when that software needs to be looked at in the future and maintained, but it also is used to generate the documentation. And it's not just an idea; it's something that because of the way the crates.io is configured, if you're going to publish anything to crates.io, you'll need to do that. Otherwise, your thing will stick out like a sore thumb. So, and it won't be very useful. So, it's very nice. It's what they call in Rust development, they call it the idiomatic way of doing things. That's their way of. You'll see that term used a lot, and if you do any online study of Rust. So the Cargo build tool also provides a built-in unit test facility, and that's very handy. And it's also customatic or idiomatic when you develop any sort of Rust code that's going to be production, that you include unit tests, so that as your code is expanded upon and modified by your organization or whatever, another organization, the test will run and tell you if you've broken anything that was previously working. So that's nice to have. Now, when the Rust compiler team releases a new Rust compiler every 6 weeks, they actually run what they call a crater run, which uses this unit test facility where all the software that's made part of the Rust tool chain, which is written in Rust, when it compiles, they do this crater run, which may take a day or two to run fully, and it detects if they've integrated anything new in the current release that breaks what previously worked, and that allows them to clean that up before they actually push that release out. It's a very, very nice thing. You rarely have new releases come out in Rust where there's occasionally, like once a year or twice a year, maybe you'll see a message come out if you're on the mailing list and using the tools where it says, oh, you need to bring down this patch. We found 3 days ago after push out the release, this one thing isn't working. Well, they don't have very many of those because of this test facility they have built in. And it's idiomatic for people's own development projects to use these unit tests. And I mentioned Rust macros, and they're a very powerful macro facility. They're much more sophisticated than what the C and C++ #define facility. And they're actually a language within a language. And the Rust language itself, the standard library that comes with Rust, a lot of the features in it actually use Rust macros, and it makes the code that you write a lot easier. Here's a diagram that shows the layout or the relationship between the various components of the tool chain. This is something I put together. If you're digging into this, I'm going to move along here, but this may be useful in your own self-study. So basically, a very powerful thing about Rust, and as it comes to doing embedded development or cross development, is that the Rust compiler is built to build cross to any of its supported targets. And most of these are embedded targets. They're the common non-embedded ones, which are like Windows, Mac, Linux, whatever. But there's over 200 embedded targets that you can build your Rust code to. And of course, if you're building your code to run on an embedded system, it's got to be designed to be run on embedded. You can't be doing things that aren't supported on a particular platform. Obviously, you can't try to use peripherals that that don't exist on your board, but you know that's just common development knowledge. The target cross targets cover all the modern ARMs, both 32 and 64 bits, modern Intel platforms, actually going back to the non-modern ones, the 32-bit ones, but also the RISC-V, both 32 and 64-bit. ESP, NRF, those are like the ones that have the Bluetooth features. Various Raspberry Pi chips, some of the older chips like MIPS, and so on. So for the full target list, you can run from a command line with the tools installed. You run this command, it will show all 271 of those targets. Okay, so again, the Rust concurrency and safety guidelines are one of the main benefits of Rust. And it consists of what they call the ownership. This is data ownership system and the borrow checker. And also it uses what they call data lifetimes annotations, where it uses, it basically the compiler allows you to annotate when you need to make a reference to a piece of data, and it allows you to do things that the compiler, so it can safely confirm that what you're referencing, that reference doesn't live beyond the scope of the thing that you're referencing. And in simple cases, you don't necessarily, well, you don't need to use explicit data lifetime tracking, but in the more complex cases, you do. So the compiler can say, nope, this is going to, have this problem if you build this code, and it prevents you from building it. And I mentioned this because once you dig it, some of you may, from your other experiences in the past and your education, may already be aware of this, but as a programmer coming from a non-Rust background, I actually learned quite a few things about how these strange referencing lifetime and dangling references issues can come up. I occasionally would run into them in C++ or where my code would just run, and most of the time, and occasionally I'd be doing something in a loop, and things would blow up, and it would turn out that I was iterating across like a vector or some more complex data structure, and I had updated the data structure in the loop. The compiler, the C++ compiler, was just totally happy with it. But when it ran, and it may have only been in certain circumstances when it ran, it would actually crash because it was trying to use a pointer that was pointing off to garbage land. And Rust prevents that. Okay, so again, the other main benefit of Rust is the low-level programming, and that's with operating systems or embedded, where you have to deal with hardware registers, raw memory addresses, DMA controllers, and such. Raw memory addresses are something that just come for free in C and C++, but they're not. That you can do a lot of damage with them if you don't use them properly. So what Rust does is they require that you can only use them in what they call an unsafe block, and you can only use them in limited ways to get what you need done, and you can do anything you need, but the controls on it prevent you from doing crazy things that, well, it doesn't prevent you from doing crazy things, but if you do, it may give you an idea of what went wrong, but also the idiomatic way of using unsafe code, which most programmers will never write. To do my embedded firmware demo that we're going to show at the end of this, I did not have to write more than one line of unsafe code, and it does a lot of things that you'll see when we get there. But when you have unsafe code, if you write it yourself, you're making new unsafe code, that code needs to be reviewed by someone other than yourself who's knowledgeable and who can assure that you've maintained the safety soundness of that section of code so that it doesn't do something that will blow up later. And that's something that the people that write the the Linux kernel do just as a matter of survival over the years. I don't know how many of you are familiar with the Rust kernel development, but there they don't have this feature, and they actually Linus Torvald, the creator of Linux, who's still the what they call the benevolent dictator of the operating system. He's in the process of having his team, his support team. They're working very closely with the Rust compiler team, and they're building up infrastructure to use Rust in the Linux kernel now. But we won't go into that now. So the Rust uses, like most other programming languages, it uses static memory data variables, or it uses stack variables, and it uses heap allocated memory. But in Rust, you don't have automatic garbage collection because that's too unpredictable and inefficient for systems code. And also, the programmer doesn't explicitly free up any heap allocated variables like you would in C++, where you do. I mean, sometimes they happen, but you can package your code where something just goes out of scope and it never escaped the scope. No references to it escape that scope, so there's no problem. But the Rust automatically deallocates things under all circumstances, and it does it very efficiently, even in cases where the reference to a heap allocated object does need to leave the scope that it was declared in. And it does it through its data ownership and borrowing subsystem. So won't go into more detail about that. That's a several-day conversation. So
we had a quick question for you.
Sure.
Does Rust support the free RTOS?
To my knowledge, currently that is not one that's officially supported. What they are just now officially supporting one called Zephyr, which is one that is it's also embedded open source embedded RTOS, but it's the one that is sponsored by the Linux Foundation. There are people who are using FreeRTOS. I've actually used it in the past, that are experimenting with Rust. But if they want to send me an email offline, I can, I'll tell them what I know about it. But it's something that's got to be researched. If that's something you intend to do, I believe it's certainly not, if you need to do it tomorrow, it's probably not a good thing. But if it's something that you're interested in getting involved in to make happen, then I'd be happy to talk with you about it. But that's the answer.
Thanks, Jerry.
Yep. Okay. I just want to quit. I know I'm probably getting behind on time here, but how am I doing on time, Sean?
We're fine, Jerry.
Okay. I'll keep it brief here. This next thing is as far as the way that Rust handles data ownership and borrowing and automatically freeing heap allocated space. I wanted to include this slide from a book, which I have a couple slides at the end of the presentation. I have a link to the O'Reilly for this book here, this Programming Rust Safe Systems Development by Blandy and team. Here is probably the best technical book if you're a programmer who's coming, wants to learn Rust. There are free books supplied by the Rust, open source system that they call the Rust book and some things like that, and those are good. But this book is excellent. It has all these diagrams and explains things. The most of the free books on the Rust sites they're just free textbooks, or so to speak, or they don't have a huge number of diagrams in them, but I find this book is excellent in the sense of what they do. They show you under the covers, and they give this example here where you have two assignment statements where you in this one this is this somnambulance to string is allocating a heap allocated string, rest string, and assign it to this string one variable. And it's on the next line, it's copying, or actually I should say, it's moving. It's doing an assignment where it's assigning this thing that it allocated here to this new string 2. And because the way Rust ownership and borrowing rules work to enforce its ability to provide safety, it actually moves this. So once you make this assignment, this variable here can no longer be used. If you were to down here try to reference this string 1, if there's a line of code here that did it, the compiler would reject that, tell you that string 1 is no longer valid because its ownership changed to this new variable. And what that means is Rust does this so that you don't end up with two different pointers to this data, so that if the string is moved and causes the data pointers to change and go to a different location, you won't get basically a dangling pointer, which means you have a pointer that's no longer pointing to valid memory. And they do this with these heap allocated variables use these thing called fat pointers, which are these very efficient, like 3-field structs. The compiler does this. You don't have to know about it, but this is showing you how it works to give you an idea of the efficiency. Well, when it moves this, it doesn't physically move the memory. It just essentially, when this variable here was created on the stack, it created, it pushed one of these fixed size objects on here, and it basically, while doing that, it moved the contents of the one here to there. So it just copied this amount here. This string, in this case, the string is just a 15 or 20 character thing, but this could be a 1024 byte string, and it doesn't copy all that data. It just moves this fixed size area, this small compact fixed size area, to this new one. So this assignment just simply copies this content to this one here, and it doesn't have to reallocate the string. It keeps this in the heap where it was before. And so that's an efficiency thing that the Rust compiler does, so that it can continue use its safety rules, and they actually work. I just wanted to throw that in there so people will know about this book that gives you all those kinds of inside tips there. Okay, so the Rust compiler, in order to be efficient and also to support all these different targets it does, the one compiler, you don't have to have 7 different cross tool compilers installed in your system. It uses LLVM, which you can if you're not familiar with that, you can Google it. It's a modern cross-platform assembly language that modern compilers use to get out-of-the-box cross-platform support. Okay, and just one other thing here. Rust normally builds binaries, your programs, which are statically linked. So they're a single file that gets, so when you run them, the installation is practically, just copying them to a new system. You can on the operating system base, Windows. If you're writing Rust code that runs on Windows, Linux, or Mac, you can still use DLLs as a packaging option. but you can also use the statically linked version, and then you just have to copy the one file. You also may have to copy any fixed data files that your application requires at startup, but that's that's normal. Okay, so here I go over a number of Rust other sort of standard features. They're data types, the data types in Rust, very briefly. Also should mention threads, also the built-in heap allocator, and certain other Rust features are actually provided by a standard library, which is called STD. And that reduces the complexity. The compiler doesn't have preordained knowledge of the fact of those features. That it basically just uses them from the library, but it's done in a way where they're just as efficient as if the compiler had built-in knowledge of them. So it comes in handy when you're building embedded code where you don't want to drag in the entire standard library because of its size. It just may not work if you don't have enough RAM. The board that we're going to see the demo on only has 32 kilobytes of RAM. So even though the standard library, a good chunk of it would be in the code space, that our embedded board has 256 kilobytes of flash, which is where the code goes. It's still, when you load the standard library, there's things that have to be initialized in RAM, and they take up space. So Rust, by putting a lot of its code in the standard library, reduces the size of code that you can use to run embedded systems. It's a nice way of approaching things. One other thing important to note, people who haven't yet looked at Rust, it doesn't have exceptions like C++ or Java and some other programming languages have. And the reason for that is that it's much more efficient to use result types and Rust or return status types. And Rust has actually, I won't go into detail here, but they have what's called the option the result type, which is a way you can return a status, which is very efficient on the stack in terms of the amount of space it takes in the stack. But when you check it, the value can either be valid or it can be an error. It could actually be either one. And your code doesn't have to do a lot of if statements and such to make that determination. It can just use a match statement, which makes the code less complex, and you don't end up with these huge, nested if then else statements checking your results. It's a nice feature. They call it pattern matching, and it comes from functional programming. For those like myself who weren't familiar with that before picking up Rust. There's also a thing that Rust has called the panic handler, and basically it's if you ever have a crash occur in your code, it doesn't just go off and never land and start running through other parts of your code undetected. It basically prints out a debug message or logs it depending on the environment you're in, and it basically stops the code in its track so that it prevents what's commonly referred to as security issues, where if someone causes something to go wrong in most programming languages, they can go off and just start executing code they weren't meant to execute, which can cause ransomware and other things that people really don't want to have happen. The thing that the demo, I'm going to speed up a little here. The demo will use what's called async mode programming in Rust, which is not the default mode, but it is available. And it's actually, it turns out in this embedded firmware app that I'm going to go show you that I put together for this demo. It's very handy because it gives you concurrent tasks, so you can have multiple things going on at once without doing a lot of complicated switching manually, like you would do in a C program, where you know, if you're in an embedded environment, you're trying to do multiple things. You have to create these complex manual state machines, or you know, do manual coded interrupt handlers to get that effect. Rust with its async and with this embassy package, which is another open source package I'm using for that we'll see. You get this multitasking for free without incurring the overhead of threads, which are pretty heavyweight when you're trying to work in an embedded environment. If you're running an RTOS on most embedded systems, you really are very limited unless you have, you know, at least 128 or 256K of RAM. You can run in less RAM, but they're generally pretty compact.
So Jerry's, are you ready for the demo?
Yeah, I think we're about there. Let me jump ahead. Yeah, I just this is a very simple form of a Rust embedded no standard app. I won't talk about that further. It's something you can look at on your own. Summarily, well, here we are. We're at the app. I'm going to show you. This is the setup I'm using. I've got a power supply that I use for powering these. I've got two serial ports that I'm using off this STM32-F091RC M0 ARM board. It's a very low cost board. It's like $30. The chip itself, I think in quantities of thousands, like 70 cents for the chip. It has 32 kilobyte of RAM and 256 kilobytes of ROM flash. But I'm using in the demo on this board, this chip also has 8 UARTs built in addition to ADCs, you know, DACs, a few things like that. Now, they're, again, this is a low-end chip, so the ADCs I think are like 12 bits. It's not super high resolution, but it's a pretty good deal for 70-cent chip, and it's industrial grade. These aren't like Raspberry Pis or whatever, which haven't necessarily been used heavily in the industry. I have several clients who use these STM chips, and they have for the last 10 or 15 years. They're pretty rugged. They come in the high temperature ranges as well. Anyway, I'm using 2 of the UARTs. On the screen, I'm going to have 2. I'm running this. My debug environment is my Windows 11. That's where my Rust compiler is, and the Rust debugger, remote debugger. And I'm going to have 2 serial terminal programs running, connected to the 2 serial ports coming out of this board. The firmware, let me go to here. This is a top view of the board. This is a diagram of our firmware app that we're going to look at. It's one of these embassy async package programs. And so in the main, where my code first runs, I do a couple things to initialize the interrupts and DMA for all the peripherals, but specifically for the 2 UARTs. And then I spawn these 4 tasks. And then, of course, the main itself is a 5th task. It's not referred to that way, but it's effectively a 5th task. So there's an LED task, which actually controls a pattern. There's a button on the board, which when I press that button, the LED is going to change. When I press the button, hold it for a second, it's going to change modes where it goes from either a slow, it's going to toggle between a slow blinking mode or a fast blinking mode. And that's what these 2 tasks take care of. And then I have for the UARTs, I have 2 UARTs I'm writing out to and using. One of them I call the command menu task. UART, it uses one of the UARTs, and it lets me type in from the terminal program on Windows a command, which command I want to run. There's 2 commands I've got to implement. One is I search through the stack of my application and look for the high water mark of where my stack has grown to during its current execution. And I do that because when the program gets loaded up here as part of the embassy setup, it writes a pattern of all CCs throughout the allocated RAM space. And I can generate, you can generate with, when you compile this from the Rust compiler, you can generate the assembly listing and a map. So you can look at how this thing is laid out in memory and see where the stack and the other things are. So these are the different tasks. I'm just going to quickly go there. We'll see the demo before we run out of time. I hear Sean coughing in the background. Thank you, Sean. Okay, so now I'm going to switch the demo, and bear with me here. Let's see here. I should have that still up. Here we go. And let me actually bring up the two. Let's see, bring this up, which is one of the screens. And let me bring up the terminal program, which is the other one. So I've got two terminal programs here. This one is what it does. It's just dumping out a lot of ASCII data. And it like what it does is it prints out these fairly long lines of ASCII text, which are about 150 lines, bytes long. And I print them out continuously in a loop as fast as I can. And then it gets to the end and asks me, do you want to do it again? I could say, if I said no, it would exit this task, which isn't very interesting for the demo. So I'm going to say, I'm just going to enter because I only exit when I see it end. So now it's starting that again. Down here, I've previously, before we started here, I did a command. Okay, I'm going to do it again. Now I executed the to command, which is a dummy command. This is a very simple demo. Now I'm going to execute the one that dumps out the stack contents. So I do that. Now it's showing all the contents. This is not something you do in a real application, obviously. But it's something I'm going to play around with to make an embedded onboard debugger, which will be, something that will be handy for some work I'm doing. So it's going to go for a few seconds. They're both running at the same time. In a moment, I'll switch to the board and I'll change the LED. Okay, so that finished. You'll see here it reached address. It's going from the effectively the active part of the stack as it grows, and when it reaches the point where I no longer have put anything further on the stack, which would be this let me do this here real quickly. Okay, you can see here when it goes from this address here with the hex A8 to CC, and then this group is the CCs. That's when I detect that that it's done that. Now I'm going to run this again just to have it busy again. Remember, these are being done asynchronously with no extra threads from the application. Now let me briefly, I'm going to show you the LED blinking by switching my camera. If I can do that without breaking. Actually, before we do that, let me just bring up the source code to just briefly show you the source code here. Okay, this is my VS Code, which I used to cross-build this code. Now I can recompile it, but I won't do that here. But here are the, let me shrink this down so it's easier to see. These are the 4 tasks that we talked about, showed in that diagram. And this is the main task where it starts up. Here I'm initializing the UARTs. This is where I initialize the embassy, and by default it initializes the default peripherals on the board. Here I'm setting up. Now I'm breaking out these 2 UARTs from this board. By default, they're not broken out. So I'm explicitly calling these are calls through the embassy to the HAL of this board, the HAL, hardware abstraction layer library that comes from STM. They provide it in Rust. And then I have some data variables here that are used to allow my tasks to interact with one another in limited ways in this case. And so here at the top level, I'm using an async loop to monitor when it goes in and out of the fast and slow blink mode. That's all this does. but it's running concurrently with these 4 tasks up here. And the LED task basically starts and it runs, and it loads one of these atomic variables at the top of the program. You'll notice these are atomic variables. That's a Rust data type provided by not the standard library, the core library.
Jerry, we got a question. Can you increase the font size on the code?
Let me try here. I think so. If I don't tap the wrong thing. Is that better?
It's bigger.
Okay, does that help? So,
yep.
Okay, let me move this down.
Yes, that was helpful. Thank you.
Yeah. Okay. Yeah. So these atomics are a way of safely accessing the data, and this load on the atomics allows this is a feature that runs on both single core systems, but you can also use this on multi-core systems. So it's got built-in what's referred to as the code ordering. So if you're on a multi-core system, you could potentially, these threads, well, in this case, they're async, but they could be, and also Embassy, that's something that's being added to Embassy as we speak. I've been communicating with the team that does this. And it does support multiple cores on Raspberry Pi. That's something that's being worked on right now, and in the future it'll be running on other multi-core ARM systems for embedded. But it will allow this data to be safely accessed in a very efficient way, even if you're different, in this case, async tasks. But if you were using threads from a thread, so that if you're talking cross-core, you don't have what they call race conditions. So that's a very nice thing. But anyway, this task, the LED task, monitors and it sees when the button task has changed the blink rate, and I print out a debug message when that happens. But more importantly, down here, I either execute the fast blink sequence, which uses this is a HAL feature of HAL function here that comes with this board from STM. Lets me toggle the current state of that LED IO. It's the GPIO actually that controls that LED. And similarly, I use it here. So anyway, we're going to run out of time here, but for anyone who's interested in this,
Jerry, we're gonna extend for the questions. We've had 2 questions come in. Okay. So why don't we kind of just move to kind of a Q&A?
Okay.
Q&A. The first question was, can you show the cargo.toml file?
Sure.
For this?
All right, I will do that.
And then John Westmoreland, I'm going to come back for your question too.
Okay. Yeah, here's the TOML. This is the cargo TOML here. And there's also of interest is the project TOML file. And that's here.
So I think question for the audience. Do you want to, so Jerry, are you going to make this into a package as part of the deck, or were you intended to distribute this piece of it or not? I don't want to
yeah, I have no problem doing that. I do want to go through. I'm using this as it's something I'm doing some active development on. So I need to I will do that. I've thought about it. I have no problem, but what I will do, I'm not going to publish a crate with it. It's something I'm going to be using in-house, and I don't necessarily want to publish it as a crate, but I will provide it the source and the entire project with a some kind of with an email that says what kind of the rough setup, what things you might have to install on your system, the tool set, whatever. But I'll need a few days to do that.
So what I'm going to put your email address back in the chat again and ask people that really want that just to contact you and then let you distribute that when it's appropriate, if that's okay.
Yeah. No, that's perfectly fine. Okay.
I thought I did that. And we had a question from John Westmoreland.
Sure.
Um,
Hi, John.
he mentioned guardrails. When you say guardrails, does that mean bounds checking is built in? Is the lint also built in? And how does this compare to PC lint?
Okay. The bounds checking is built in. You can, if you can disable it by taking some, with some bill switches or feature switches. Um, if that is like if your performance is that critical, you can do that. But the recommended way of doing that is that you first test your code, give it fairly good coverage testing, and make sure that any unsafe code well, it would only be unsafe code really that you would have to worry about. If you don't have any unsafe code, yeah, you should be able to remove the balance checking anyway, the runtime balance checking. But if you have any unsafe code, you'd want to test it carefully, then remove the balance checking. Yeah, that's doable. As far as that particular lit you mentioned, I haven't used it, so I can't speak to that. I've only used the Rust lit. I've used I think Lint on Linux a few years ago, but
Okay.
okay.
Jerry, do you have
John,
a GitHub repo?
I do, but I haven't really published anything on it to date. I worked on other people's. I worked on a couple of serial crates on Rust open source crates that are on Crates.io as a volunteer a while back. But yeah, I do. But I haven't.
There's a question for someone who's experienced with C, C++. What are the key challenges that might be difficult to grasp, and what resources are available for learning Rust if they're making
Okay.
the jump from C, C++?
Okay. Excellent question. I have. There's a slide. There's two slides at the end. Let me switch back to the slides.
Okay.
If I can do that here easily. Okay. Let me go here. I'm gonna start again if I remember already. Oops. Give me a second here. I lost my mouse. It's something. All right. Here we go. All right. Let me go to the end quickly. Okay, this is the book I mentioned. This is an excellent book, and these guys are old C++ guys, so that's a good one. Also have these resources, which are good. There's a ton. I mean, just frankly, there's a ton of YouTubes, and there's a fellow, Jean Ginzet, he's Norwegian. He finished his studies. He was a graduate student at MIT. Was one of the early contributors to Rust. Worked on the compiler team. Still is involved with that. He appears at some of these Rust conferences. He's got these excellent live streaming. I mean, they're recorded now, but live streaming what he calls deep dives into Rust, where they're excellent, and he also is a C knowledgeable fellow. Someone, if you email me, I can. I certainly. I may not be able to answer your email immediately, but I certainly will do it. Quickly.
So some folks have put some other resources in the chat. There's a question. Are there good resources for developing Rust for embedded systems?
Are there good resources?
Yes.
It is one of the sort of newer, not new in the sense that it hasn't always been there, but it's one of the emerging areas of Rust. I mean, using Rust for developing desktop applications, with the exception of GUIs. GUIs. That's I've got a couple slides previous to this where I talk about that. GUIs are right now you have options of cross-linking to or linking to Qt or to there are some scaffolding libraries to some others, but embedded is the area that's also still an emerging part of Rust, and the resources are growing on a monthly basis. But if you're going to be doing a commercial project that you need to have results, that you're trying to produce a commercial product or a medical instrument that you need to have ready in 3 months, don't use Rust for it. You probably shouldn't do it anyway, especially if it's a medical project, if you've got to get it done in 3 months. Actually, while I'm thinking about it, let me go back to that slide. Well, here, this one's about the GUI, but you can look at that. But okay. Here, if your project is either poorly funded or has a very tight completion schedule, or has legacy constraints where you have to pull in a bunch of old legacy code, then you really need to check it out. I mean, Rust, it has its benefits, but when you start pulling in non-Rust languages, they're automatically considered unsafe, which in effect they are. And so you're going to be limited, and you're going to have more challenges and more legwork to do. So on a tight schedule, or if you've got a low funded project and it's not being done for your own fulfillment or or your long-term business plans, probably not a good idea to go with Rust if you're on a shoestring budget or a very tight time schedule. And as well, if this is the second bullet item here, I mentioned that if your project management is conservative, and for good reason possibly, you want to not kind of force Rust on them. Obviously, you're not doing anyone any favors. So, in the case of the question about embedded, I would definitely recommend that you do a what we might call I don't know, not a trial balloon project, or what would you call it, a prototype project, or a research project in-house, and see how far you get. That's the best advice I can give you without knowing more about your project and getting engaged with you.
So Jerry, that's a focus area for you. So you'd welcome any emails on the use of Rust for embedded, though, right?
Yeah. I'm certainly open to discuss it, and if the right thing came up, I would be I'd consider participating, but that's not my main focus. I'm basically acting as an open source contributor at this point. Okay.
We've had somebody enter the waiting room, but I think we're closer to the end of the beginning, so we're not gonna take on new visitors.
Okay.
But I think we have time for a few more questions if people have questions. I'll put just a little plug in there about Patka, and then if other folks have questions. So question from Matt Gomez. Hello, Jerry. Would you say that there's a strong industry demand for developers with knowledge in Rust that is currently not being met? So if you had to assess that, how would you assess that?
Strong. It depends on how you interpret strong. I think it's fair to say that you could find that you're more likely to find C and C++ jobs out there, but that you obviously need to be willing to deal with a lot of legacy code. There are Rust projects. I mean, if you go on Indeed, if you go and just Google the web, LinkedIn, there are Rust projects out there. Some of them I've seen, just to give me my own thoughts. I think some of them may be kind of crazy where they expect you to be sort of an Elon Musk level developer who's going to sit down for 3 days and crank out a new operating system or something that's production level. Not to say I dislike Elon Musk. I'm just saying that because he's known to be a really hard driver. In any case, there are jobs out there in Rust. You can find them on the web. There, some of them are for crypto, jobs. Some are for aerospace jobs. Some of the self-driving cars companies, Tesla, Chrysler, Daimler, some of the others I've seen posting jobs for Rust. A job. I won't say huge amounts. Now there is a resource. There's a newsletter that comes out. It's I think supported by the Rust, either the Rust Foundation or the Rust community as a whole, called This Week in Rust. And anyone who's interested, you Google the phrase "This Week in Rust," or if you email me, I can send you a link. I don't have it in front of me to register for that. But it has all kinds of information. One section in it every week is past week's jobs in Rust, and it's not a detail. I mean, it's not. It doesn't necessarily give you the actual link, but it tells you what companies have posted job information on the web. So that's something if you're looking for a Rust job, that's something you can consider.
Well,
I
any other been a lot of interest. We put Jerry's email in there. You're welcome to join Patka. And we've got some other comments in the chat. But I think we've covered everything. I put a link in to Jerry mentioned the This Week in Rust. So I'll give people another minute to grab that if they need it. Jerry, I want to thank you for a very provocative and thorough presentation on Rust. I think you've sparked a lot of people's interest and ideas.
Okay,
and,
well, I enjoyed it. So if feel free to reach out to me by email if you want to. I'll get to them as I can. And thanks everyone for joining, and thanks to Sean and Teresa for putting this on.
All right. On that happy note, I'm going to.
Okay,
so we'll post a link to the video and a link to slides on the Patka website next week. I want to thank everybody for coming, and see you next time.
Yeah.